So last time, what were we doing last time? That's 3 whole days ago. So remember, we were talking about putting a PL structure on a manifold. And we now know how to straighten handles except for 3 handles. So if we wanted to put a PL structure on a manifold, we might, here's a manifold, some manifold of some dimension, n of dimension n, say, and we map in a chart. So there's a chart, U alpha, this is Rn. So there's a chart, and then you have maybe another chart, H beta for that chart, and the U beta, that's a chart. And now if you wanted to make this a PL manifold, you'd like to make the overlap PL. And what that really means is that you go in from Rn into the intersection and back out. Either way is okay. So let's say you go H alpha followed by H beta inverse. And that's defined on H alpha inverse of U alpha intersect U beta. So if you take the intersection and you bring it back here, then you can define H alpha on that, and then followed by H beta. So this is an open set in Rn, and it's a map. It's the image of this is H beta of H beta of, let's see, we're going back here, so it's H beta inverse of U alpha intersect U beta. So anyway, it's a map from Rn, open sets from Rn to Rn, just this composition. And now you'd like to make that composition, you'd like to isotope it to a PL in a homeomorphism. You would isotope. Question for the audience: does isotope and homotop have an E in the end or not?
I think it does.
Yeah, probably.
I don't know, based on this argument.
Okay, we would like to isotope that composition, H beta inverse H alpha, to a PL homeomorphism. Or smooth, whatever category you're working in. So you would like to do that. And of course, you'd like to, if you've already done something, made something PL, you'd like to keep it PL there. You'd like a relative version of that as well. But that's the basic thing you want to do. You would like to make that into a PL homeomorphism, and then the charts overlap in a piecewise linear fashion, and you're off to the races. And so you can do this, if you don't run into 3 handles. Because of course, this is an open set in Rn, and therefore there's a triangulation on it. And from the triangulation, you get handle body structure, and it can be as fine as you want by making the simplices very small. So you can you don't have any trouble with epsilon. You always need to throw away a neighborhood in this subject. But so you can do if you don't run into 3 handles, but there's no reason to assume you wouldn't, and that's not a very good hypothesis. You can't, a theorem that says we're going to put a PL manifold, PL structure on N, as long as we don't run into 3 handles. Well, that's not much of a theorem. It's just not precise. You can't do anything with it. So what's coming up? This is kind of an advertisement for the next few lectures. Is that we want to apply homotopy theory to get a nice statement. The nice statement is that N has a PL structure if an obstruction in the fourth cohomology of N with Z2 coefficients vanishes. So now we've turned this into a reasonable statement. You look at the fourth cohomology, and maybe you can calculate the obstruction. And so then that's a usable theorem. Whereas this other one about not running into three handles is not very usable.
What are the handles of n? I'm sorry, I'm not quite.
The handles, you're trying to make this composition.
Yeah.
PL. And
Right.
so the handles come from the triangulation of, an ordinary triangulation of R.
Oh, I see it. Oh, sure, of
Yeah,
course.
Yeah,
Got it.
that's right. Okay.
So that was the picture of the double bicentric subdivision and all that.
Yes, that's
Great,
right.
great.
That's right. Okay, so then, so how do we get from this geometric theorem about the about handles? You know, it came from the big diagram with the torus trick, and Wall's theorem told us we had a problem with three handles. So how do we get from that fact to a statement like this? Well, the outline of this, and you know, filling in the gaps will take a little while. But the outline is that first, try to lift the tangent bundle. Now this is the topological tangent bundle up in to a PL bundle. Or it could be an O for ON, or for the differential to the diff and O are the same. So you can, if you like to think about differentiable things, a lot of this works just the same way. So you can think of a smooth manifold there, smooth bundle if you want. So you first try to lift. So you try to make the tangent planes in a sense overlap piecewise linearly. That's what you want to do, and that's easier. That's a homotopy theory problem, rather than actually trying to make the actual charts overlap piecewise linearly. So, what does this mean to lift a bundle? Well, the tangent bundle. So here you've got your space. This is just general bundle theory. You've got a space, and over it you have all these fibers. And what do you know about a bundle? Well, you know that on this open set, the bundle is a product. It's trivial. It's this open set cross the fiber. And then on this open set, it's the same thing. So it's a bundle is a locally trivial thing of that sort. But then when you take two trivializations, and you have two of these open sets that overlap, you take these two trivializations, now the fibers are glued together by what? Well, they're always glued together by a homeomorphism. And now the issue is, how good can you make that homeomorphism? Can you make the homeomorphism PL? Can you make the homeomorphism to a diffeomorphism? Can you reduce it to make the homeomorphism a linear, element of ON? Can you make it an element of SUN? The UN, make it a complex bundle. There's all kinds of things you can do. And so the way that you glue together is by a homeomorphism. They sit inside the homeomorphisms of Rn, and then there's all these other things inside. So the structure, what you say is the structure group for a top bundle. This is just the abbreviation for corresponds to PL and diff and so on. For a top bundle is just the homeomorphisms as well. It's the homeomorphisms of Rn. Might as well fix the origin. But this is by definition, this is what we call top N. That's the name we'll use from now on. It just means the homeomorphisms. So that's the structure. That's how fibers are glued together in just the world of topological manifolds. But then, so what does top N include? Well, top N includes PLN, whatever that. So this is a infinite dimensional object, but it's a group. It's a topological group. In other words, you can compose homeomorphisms. You can compose elements of this. You got other ones. there's an identity, there's an inverse, just the inverse homeomorphism. And all that varies continuously. So it's a topological group. PLN is also a topological group. You can just compose PL homeomorphisms. What I remarked about once was it doesn't have a naturally have a linear structure to it, but that's all right. It contains those. It also contains diff, the diffeomorphisms of Rn. And this deforms homotopy equivalent to ON. Let's make everything orientation preserving so I don't forget things, or not. Just remember there's no real problems, but sometimes you want things to be preserving orientation. So for the moment, I guess we don't have that. This is a theorem that these are the same, so that's why you don't usually see diff and you usually see ON when you're doing bundle theory. And then if you wanted to, you could put in UN. And then sometimes you put in finite groups. You might put in Z2, or reduce the bundle to something, an actual much smaller group. And sometimes a bundle is made with a very restricted set of ways of gluing fibers together.
I guess O is defined to fix a point as well. A fixed base point.
Oh, yeah, what do I mean by, well, no, what I said is, I think what I said is okay. What was your question?
Maybe it doesn't make sense actually.
You were asking about fixing the base point. Well, Z2 would typically, here, it would just act by reflection, which would fix the origin. That's. But you can put various finite groups in here, so there's all this structure, and so when you want to lift a bundle, you want to lift it, you're like lifting it, well, in this sense it means reducing it, in that you're taking the bundle where you're using lots of different homeomorphisms, and now you're changing, you have the same bundle, but you're changing the way you glue together so that you use a more restrictive collection from a smaller group. So therefore you're reducing the size of the structure group to smaller groups. So that could be called a bundle reduction. But the reason it's often called a bundle, often talked about lifting, is that we have classifying spaces, and then it looks more like a lift. So we have B top, say N. And so topological bundles over just a space X are classified by a map in there. And over that is a total space, sometimes called E top N, with fiber N. So this is the base space, and this is the total space of a classifying space for top N. And then if you have a map F, that map F will pull back this bundle onto X. I don't know I don't know how much bundle theory to go into here.
Well,
what do you think?
No vector bundles, I think, but that's about.
Vector bundles. Well, it's all
It's
the
just
same
like-
thing as was vector bundles. It's really the same thing.
Everybody's brought up on Milner and Stasher these days.
Yeah, okay. Well, there's nothing new here. So this is the classifying space. And now, for our purposes, we have, we have a map from B, PL. So PL, I can put an N in. By the way, I should just say this once. Every homeomorphism of Rn extends to a homeomorphism of Rn plus 1 by crossing, just by the identity of the extra factor. So you can keep on going. and you end up with just top, which means a limit of this. So I may put, if I put the n in here, don't put it in. Actually, I kind of don't want to put it in. So this is the classifying space of all bundles of all dimensions, fiber dimensions. And then that maps into the top, simply because PL is included in the top. And so I want to, so if I have a map, I map X in here. I'd like to know whether it lifts, whether I've got a bundle just built with homeomorphisms. I'd like to know whether I can build that same bundle using PL homeomorphism, which would be a nicer bundle. And the obstruction to this lies in top mod PL. So this is just a quotient group. Think of it that way. So why is, how do you understand this lift? Well, just think of, just here's a very simple picture just to give you an idea. There's a Mobius strip mapping to the circle. And if I have a circle and a map in here and I want to lift, well, what could go wrong? Well, I lift it on a point. So I lift, let's say, to that point. Lift to this point. Since I drew it that well. So I lift to this point. Well, so having defined it here on the zero skeleton, now I want to extend on the one skeleton. And you see right off that it doesn't work, because I either go and come back around to here. And that's what always happens this is the fiber. And the obstruction here lies in that you can't extend over this one cell because there's some zeroth homotopy of the fiber. And so you've got a one cell, and the two endpoints end up in differing in pi naught of the fiber. Well, so this is, so what's going to happen is that we're going to see that pi 3 top PL is Z2. Well, let me put it this way, pi k is 0 or Z2. This is for k equals 3 and k not equal to 3. So just one case. There's just one case in which that homotopy group is non-zero. So therefore, when you're trying to lift, see here the obstruction was on a one cell and the obstruction lay in pi naught of the fiber. Well, here there's going to be a four cell. There'll be a four cell mapped in, and when you, it's already defined in the boundary, and the boundary is going to go around an element of pi 3 of the fiber, and if that element is non-zero, then it won't extend. So the obstruction is going to lie, the obstruction to lifting of the tangent bundle M to a PL bundle lies in H4, the cohomology of M, Z2, where Z2 is this pi 3. So there's where the 4 comes from. Just by analogy with a simple picture over here, it's if there's a group here, in this case it's pi 3 of the fiber, so it's not a 4 cell, you can have trouble because the boundary can go around that 3 sphere in the fiber. Now usually, if you look at, this is PL over, this is top mod PL. If you were to look at, say, diff mod PL or diff mod top, Then there's lots of non-zero homotopy groups, and you don't have anywhere near as clean statement. It's kind of an unusual world where there's just one non-zero group, and then you get a very nice statement like this.
Were you very surprised when it came out like that?
Well, yeah, well, this, actually, so I knew the Torah, Torah and Larry Sieben and I had gotten together and were doing this kind of stuff. He knew more about it than I did. Anyway, we got to this stage, and I thought to myself, well, we're on a roll here. We've done all the handles except three handles. Let's do the three handle another way or do something. So I was trying to sort out three handles. And I think Larry's perspective was sort of the opposite. He was looking for a counterexample, which, well, anyway, he was, and he found one. So
Yeah.
that was, but anyway.
Will you describe it later?
I will,
Good.
yeah. So, all right, now so now you've got the bundle lifted. Well, so what? Why is that such a good thing to do to get the bundle lifted? Now we know that you have this tangent bundle, and the fibers can be made to be glued by PL homeomorphisms. But how do you get from that to actually making these charts overlap piecewise and linearly? So you got to go from the so this is a common problem in mathematics, this kind of thing. Well, what it turns out is that if n mapping to V top lifts to VPL, then there exists a PL structure on M cross R, some S. So if you cross the manifold with S, then you get a lift. Now, this is, I want to come back and do that more carefully, but let me just give you an idea as to why this sort of thing should be true. In fact, let me say it for the smooth case where you'll see it better. So suppose we have, this is just so this is our, how do we get M here? It's an N. So this is N embedded inside some high dimensional Euclidean space. You can embed a smooth manifold. So this is a smooth N. And so it has a normal one. So this is its normal bundle. I've just drawn it there. Now, I have a map. From F well, we know it was smooth, so I kind of forget that. We have a map from N into BO, because we're just working in a smooth world here. And actually we have there's this normal bundle, so if you call that E of the normal bundle of N, E is a total space. So you really have this sitting inside E of the normal bundle. And that whole thing maps to BO because this is just an inclusion. This projects down, it's a normal bundle, so it projects to N and then maps to BO. So you have a map from there to BO. That pulls back. This is really, has really got a dimension. Now I want to have some dimension. I don't know, some other layer. It's got some dimension there. And so we're taking, this is the tangent bundle. Well, it's really, I suppose it's really N. So we have this map into BON, and that bundle pulls back to the total space. And this is, so it goes back to this total space. And that means then that the bundle over this total space has a smooth structure. But what is that bundle over this space? Well, if you look at a point, here's the normal fiber, and then here's the tangent fibers. You've taken the tangent bundle in at that point and pulled it back over the fibers, over this normal fiber. So you've got all the tangents going out this way. Well, if you take the tangent bundle in one direction, and then the normal bundle in that direction, you've got basically the Whitney sum of them. So this thing is really tangent bundle of n, Whitney sum the normal bundle of n, which is a trivial bundle. So this is the whatever dimension. See, this is in RL, so the normal bundle is L minus N. And then the tangent bundle is N, so it's N plus L minus N, so this is just the trivial L bundle. Which means that this whole thing which is smooth is N cross RL. It's smooth. Now, N was already known to be smooth, but forget that fact. Just forget that fact. Suppose that you didn't know that N was smooth, but that you had somehow gotten a lift into BON. And then that lift, actually you have a lift of this whole of E into BON. So you don't know, forget what you know about N. You just got a lift, you got a map of this total space to BON. And the fibers, I just said this, but the fibers at a point are the tangent planes. So as you move along this, the tangent planes vary as they do. And here the normal planes vary as they do, but together it's this Whitney sum. So when you have a smooth structure on this total, on all of this, remember this is a smooth manifold. It's a Grassmannian, it's a finite dimensional smooth manifold actually. And this is a smooth manifold because it's an open set in RL. So this might as well be a smooth map, approximated by a smooth map. So that's what pulls back a smooth structure on the total space over this. And a smooth manifold mapping into the Grassmannian, that's smooth. And when you pull back the bundle, you get something smooth on this object. And that's why N cross RL is smooth. So that's how you get from a bundle lift to a structure on the stabilized manifold. So I'll come back and say this again in another lecture, and at that time I'll do it starting with a topological. You know, I mean, I actually just said it here. I mean, you could have started out with a map to be top. And now, if it lifts to a map to BON, I just told you how to put a smooth structure on this topological manifold cross RL. I mean, I could have started there. I could have started with this map. If there's a lift, then there's such a structure. Same thing if this is PL, BPL, same game. Exactly. I mean, at least this gives you the idea. The idea is that you've got BON is a smooth manifold, so we can talk about a smooth map into it. Well, but N doesn't have a smooth structure. Okay, well, where is one? Well, you embed N. Oh, well, I said something. If this is only topological, I don't have this normal one. But I have something that's going to be as good. But I haven't told you about it, but it'll be good enough. So then, this is smooth because it's open in Euclidean space. This is smooth, so we got a smooth map, and you have a bundle which is put together. You have copies of Rn put together by smooth maps, so that's a smooth object. Pull it back to here, and that's smooth, and that's why this has a differential structure, and that's why that's smooth. Anyway, we'll come back to that, I'll say it all again, and then just put some more details in. So now we have a PL structure on that, on the in-cross area. Then, the last step is, bring the PL structure on M cross RS down to M cross R S minus 1, to M. Bring it down one factor at a time. So there's a theorem that says, product structure theorem that says you can do that. So those steps, so these are sort of 3 steps here. You've got to know, you start off with a topological manifold and its bundle map. And then you want to know if you can lift to a PL bundle, and there are the instructions. So that's one step. Once you've got it lifted to a PL bundle, then you play this game and get a PL structure on N cross RS. And then you use this theorem that you keep knocking off factors, splitting off factors till you get down to N. My N's keep turning into M's. Pull that back down.
That's the bit which uses Laris thesis.
Which
uses Laris thesis.
Which does?
Does the
last
skipping?
step?
Yes.
No.
No, it doesn't. You mentioned Laris thesis a few lectures ago.
I did that. And
The
then
last
you-
step,
you
maybe.
Putting a boundary on that punctured torus with a PL
Yes, but
structure.
also not in this context.
No, this argument,
No.
for this sentence,
Mhm.
which is, it's going to be called the product structure theorem.
Mhm. Why? Okay.
This is that theorem, and
That's not.
product just says that this is a product and you keep knocking it down.
Is this true for all dimensions of M?
No,
What-
because of wall,
Yes. So you,
whenever the wall appears, we have to leave out dimension 4.
okay.
We have to leave out dimension 5 if there's a boundary.
Mhm.
I'm not full of boundary, we don't want to do. So, yeah, so I haven't been saying that, so, as soon as surgery appears, omit dimension 4, and 5 if the boundary of our manifold is not empty. Because then the boundary could be dimension 4. 5 manifold boundary would be dimension 4, and that's not good.
Yeah.
So I'm going to forget this at various times, but
Yeah.
you have to know when to put that in. Okay, so that's sort of the
Big picture.
yeah. I mean, I should probably come back and say all of that all over again. Okay, so now the first step, so I'm doing, to do this in reverse order. I have to think more about this step. And this is, well, so the main thing to do up here is to calculate pi k of top mod PL. And that's done actually quite nicely and geometrically using immersion theory. So you'll see how that goes. So you'll see a nice proof of that. The bundle theory, the classified spaces and so on, I don't have a lot more to say about. That's sort of standard stuff. It's just, there's a particular case of it. So, in the future, we're going to calculate pi k of top mod PL. I have to give you more details about how this works. But for now, I want to to the product structure theorem because it almost doesn't use anything at all. It almost doesn't. Anyway, and so we'll do that, we'll do this first. And then also because this has nice applications to transversality, the existence of handle body structures. Topological manifolds have a well-defined finite type, topological invariance of wide torsion. All those things are corollaries, not hard at all, of this theorem. So that's what I want to get to. But the helper theorem for this is something called the concordance implies isotopy theorem. So, concordance implies isotopy theorem. These things, these two theorems are written down well in first essay in the book Kirby7. So there's a reference there. So what does this theorem say? So remember, we wanted to solve these handle problems. We do this, go through this torus diagram, and at a certain point we have a PL structure on BK across the N torus, which is nice in the boundary, and we'd like to know whether it's PL homeomorphic to the standard one, REL boundary. And that's where we use Wall's theorem. Well, suppose we don't want to use Wall's theorem. What other hypothesis would enable us to take this handle and straighten it? Well, if it's concordant, then we can. So, we say, okay, handle with PL structure, let's say sigma, standard on the boundary. So this is BK cross Rn with the structure sigma. And on the boundary, SK, or near the boundary, neighborhood of the boundary, this is the standard PL structure. So you have some PL structure. Is concordant to BK cross Rn. When I don't specify a PL structure, I mean the usual one. Say that's concordant to that if there exists a PL structure on I cross BK cross Rn, standard at the zero end, and sigma at the one end. So we got I across our handle problem. And on one end, everything is standard, and on the other end, you have sigma. And in the middle, well, the concordance says in the middle, this PL structure doesn't have to respect the I factors, the T factors as you go along I. So you've got, that's why it's weaker than just saying, well, yes, it's weaker. So if you think of this handle as, so here's our handle, and it's standard here. Our little neighborhood, and then it's something inside. That's sigma. Well, then you could cross with I. I should do this in the wrong order. So this one is standard everywhere. And then you just have something in between. And this is just, it's wiggly, it's whatever it is in between, it's just some PL structure in between. So that's a concordance, and now the theorem says that if you have that concordance, then you can straighten it out. You can take the standard stuff and you can just kind of move it across. You can straighten it out, and in particular, you can straighten this handle you didn't know much about at the other end. Remember that our problem is always, you've got this PL handle embedded somewhere. You've got this handle embedded and you pull back a PL structure on it. So let's see. Use an extra black one. So just briefly, here's our standard picture. We've got BK across on the end. We have H going into some PL manifold Q equals K plus N. And it had a PL, that had a PL structure which we pull back to what I call sigma. So this has some PL structure, theta say, and H is this embedding. So we pull back that PL structure to sigma. So that's where we start over there. And now remember, you try to lift it. And you run through the tori, you get it up to BK across TN. And here you have the punctured one. And you got a structure sigma 1. And now, the fact that, okay, we've got this structure, and now we want to know, we wanted to know, is there a PL homeomorphism to BK cross TN standard? We wanted to know that. And that's where we were introducing wall. There was an obstruction, we took a two-fold cover, and we got rid of the obstruction except for one case, for 3 handles. Well, so if we don't have wall to apply, how would we know this is their PL homeomorphic? Well, you go over to this hypothesis, and you use the Escobar-Mortensen theorem. Because here's a PL manifold. This direction is the I factor. That's the I factor. Here you've got something standard. Over here you're not sure. Well, what is the Escobar-Mortensen theorem? Well, sorry, you don't have the Escobar-Mortensen theorem yet. This is Rn. I want to carry along this concordance up to the torus level. So these two this guy and this guy are concordant because we lift this concordance all along. In other words, when you have this immersion alpha, well, there's an I factor coming out of the blackboard. And you just cross with the identity of the I factor. So you lift the whole concordance up. You just lift the whole concordance up, and so you have a concordance here. And then you apply the Escobar-Mortensen theorem. So in this picture, imagine that this is now not Rn, this direction. That's not Rn anymore, this is the N torus. So it's BK, B1 across the N torus. And there's a B1. So K handle, 1 handle across the N torus. There's this concordance. Well, the Escobar-Mortensen theorem works perfectly well here because that's exactly what it's a relative Escobar-Mortensen theorem because you've got the boundary down here, but that's fixed, and so that's not a problem. And that just says that this is PL homeomorphic to a product. And that PL homeomorphism can agree with what you've got at this end, and it moves this around. But it's a PL homeomorphism. Well, that solves the problem. This This end then, which is what you see right here, this end is PL homeomorphic to that end. And so you get this because of the concordance. And then you proceed as before.
Could you repeat why they're concordant?
Why? So the concordance, it enables us to apply the Escobar-Rosen theorem. So these two guys. In the picture, this is my right hand and this is my left hand. If you go over here, these are these two ends. These are the two ends. Now, at first, this was just an R-end fiber, but then we went up to the torus and we have a torus fiber. So these are the two ends, and there's a PL structure between them.
Why?
And so the PL structure comes from the concordance. That's the hypothesis. So it's concordant if there's just a PL structure on I cross BK cross RN. It's standard at this end and the sigma at this end.
So you're assuming that concordant?
I'm assuming it's concordance,
Okay,
right?
okay.
Yeah, that's
Well,
right. That's right.
that actually is on the blackboard.
Concordance is what implies this. So we assume the concordance, which of course is a real assumption. It's, it's a big assumption because you're getting something just from the Escobar-Rosen theorem, nothing harder than that. So it's a big assumption. So, this is the point. This is really follows from this just better geometry and follows from the Escobar-Rosen.
Also high dimensional, but for different.
Yeah, we need high dimension here. Got dimension 4. So that says, I like to just put this in the phrase of solving the handle problem. You'd like to straighten means make it PL. You'd like to straighten this handle. You got this embedding into this PL manifold. You'd like to straighten it. And it says you can straighten it if you have a concordance. Which after all, this, as I said, is a real assumption. However, that does enable us to prove the product structure theorem. And I don't suppose I should start in on it now.
Perhaps not.
Perhaps not.
What? But describe what you are going to be doing. Don't do it.
So just to give you a hint for next time.
Exactly.
So we're going to have, I'm going to do the case when S is 1.
Okay.
I guess it's very top up there. So just, all we have to do is knock off one factor at a time. So we'll just start with M cross R. And it's got some structure. And we want to get to end with the structure sigma cross R. So in other words, we want to alter this so that it looks like the PL manifold cross R. Then you can just, or after the PL manifold, you can just forget the R. So we want to do that. And well, let's see. It's subtle. I had to spend a while today trying to remember how to do it. In fact, I won't, let's see. I mean, the idea is going to be, here's N. I'll draw it two-dimensional. And here's the R factor. And we have a PL structure on this thing. So that means that N is actually wavy. It's not linear. It's not PL. It's just whatever. And there's a PL structure, but N is not a nice PL subpart of it. It's because it's just like a, it's just, so what you see is you see some charts down here. And, well, So let's suppose that you made N nice and flat. In other words, you've got a PL structure there, and then it begins to get wavy. So this is, we're gonna have a compact set here, and an open set around it, U, where we've already gotten in to have a PL structure on a compact set, in fact, on a neighborhood of it. And then we wanna know about another chart, really, where it's wavy and as part of it is like this. And we want to know how to how to adjust this global PL structure to make it a PL structure on M cross R, or PL structure on this chart cross R. So it's a chart by chart thing again. Well, it's really two applications of the concordance implies isotopy theorem, because if we take this chart, and this is the zero level, and up here, at a higher level, where we don't touch this, we think of this chart just as our Rm plus, we take an Rm plus 1 chart up here. In other words, this chart crosses an open interval. And this chart is a copy of Rn, crossed with R is Rm plus 1, and so that's like a zero handle. So you just wiggle that zero handle so that it becomes flat. So now up here this thing really looks nice and flat. So what you've done is change theta here. But now how are they related? Well, you've messed up the good part here. So here's still C, and U is bigger. But the PL structure you had down here and the one you have up here are different now, because you wiggled this one. It was something that went all the way like this, and you made it level so that so the charts are put together this way, crossed with R. So first we have to use concordance implies isotopy, where the I factor is running from 0 to 1, and you take care of this things over C. So there's now standard over that part. And then, after that, you look at, say, for example, on one handle, same one handle, and it's nice on the boundary because of what I just said. And now this part's wiggly, but this part is in the level. So that's the good part, this is the wiggly part, and you've got a concordance in there, comes from theta, and so you use concordance implies isotopy to fix up this handle. That's very briefly how it goes. So I'll say that with more care and so on at the start of next time. And then, well, why are you doing this? So here's 30 seconds why there's handle bodies. You've got your manifold N. So here's a chart. That's Euclidean space, so that's a handle body. So you take a large part of it, and that's a handle body, H. Now you take another chart. Well, here's the boundary of this handle body is codimension 1, so it has a nice neighborhood. This chart, make it smooth, so it has a smooth structure. It's a smooth structure theta again. It's got a smooth structure. That puts a smooth structure on this manifold cross R, because there's the R factor. In this thing, it's just a topological manifold with a R factor. Now you use the product structure theorem to say wiggle it so that this becomes, you're changing this, and it becomes smooth in this structure. Well, then if it's smooth in this, so in other words, you take this structure on this submanifold L cross R, and you make it into a smooth structure theta crossed with R. In other words, you wiggle this to make it smooth. And now that it's smooth in here, this is inside Euclidean space, you've got a smooth submanifold, you can have nice, you're in the smooth world, you can make that a handle body and go out as far as you want. And you just did it. So all that is that, and that gives you handle bodies in every dimension except for where it's false, so I'll tell you why it's false. So that's an application, you can see, you can sort of see at least how easy it is to prove something like that once you've got the product structure theorem. So the product structure theorem is a good theorem. So much more about that next time.
Thank you.
Thank you.